Everybody, welcome to the last session of the VMIL workshop. We'll have 3 talks in this session. We'll also have some closing remarks from Andrea at the end, I think, I hope. The first talk will be about how to collect garbage in blockchains, and Luke is going to be the presenter.
Thank you very much, Adam. So as already said, the talk is about blockchain, and we focus on a new trend of blockchains, namely compute blockchain, general compute blockchains that can be perceived as some kind of a new virtual machine that is secure and distributed at the same time. The idea is that the computation is taken and then mirrored, replicated across different computer machines. And of course, because one cannot assume that all computer machines perform the task in a faultless way, and also there may be malicious node, there's Byzantine fault-tolerant consensus that takes place on the computation. So there are several application cases. One of, let's say, foremost cases is obviously decentralized financial exchanges, also smart contracts, decentralized autonomous organization, cloud services, but there are other applications like decentralized social media and so on. To focus on blockchain, the runtime model is a little bit different to classical computing. Also, one can usually program in a high-level programming language, but underneath there is a transactional execution model, meaning that a program that is deployed on a blockchain runs a series of transactions underneath, and the transaction is nothing else than a sequence of deterministic program operations or program instructions. Determinism is important, such that the distributed compute nodes can reach consensus in a repetitive way. A transaction itself has access on the program's main memory, and that main memory is persisted on the blockchain, meaning that a transaction somehow transitions the memory image from one version to the other. Of course, at the implementation level, there can be optimizations. For example, there can be differential memory image snapshots being taken. Also, like modern blockchains are able to truncate the memory image history in a secure way, so there's no need to retain the whole history to replay that from the beginning. Our focus is a little bit even more specific. We focus on the internet computer, which is one of these general purpose compute blockchains that uses WebAssembly as the virtual machine, so the common denominator for various programming languages that can be executed, can be used as platform for that blockchain. Of course, the set of features is restricted to deterministic features, meaning that, for example, and that matters here in that talk, no parallelism, and we also do not use multi-threading for the programs. Currently, the standard of WebAssembly, although there's a proposal for 64-bit, is on 32-bit. That means that the standard model for programs executing is that they have a main memory with 4 gigabytes. There's separate memory, but I don't discuss that yet. It's out of the focus for that talk. For the internet computer, there's also fairly new programming language called Motoko. That's a language that is specifically designed to ideally fit the concepts of the blockchain. Of course, there's also support for other programming languages. Motoko itself compiles the WebAssembly from the language model. It's very similar to TypeScript. The Camel has been specifically designed in order that there's high resemblance and easy start for programmers that want to work on that. It's object-oriented, imperative, functional, asynchronous, and what matters for this talk, it's memory safe, and therefore also garbage collector, meaning it uses an automatic garbage collector to reclaim memory. When we look at garbage collection, there are a little bit specific requirements when it comes to a blockchain. One of the aspects, I guess the most important one, is incrementality, namely that these transactions that I mentioned, they impose a very strict limit on the amount of computation that can be done. That's for different reasons. That's one of the reasons it's that these consensus can take place and these memory images, the logical memory images can be taken, and that's implemented by having an instruction limit. That's a very hard limit. Whenever computation takes longer than this limit, sometimes also called gas, then the computation is canceled and the effects are rolled back. So it's important that garbage collection work must fit into these transactions. So a simple approach of just having a stop the world garbage collect is infeasible because maybe the memory complexity is higher than could fit in a single transaction. It's also not possible just to span the transaction work to the next transaction because there's always mutator work in every transaction. Mutator work is actually what triggers these transactions. There's another aspect which I think matters on the blockchain, namely the longevity of the programs. Programs that are deployed once on the blockchain conceptually live perpetually, so they have infinite lifetime. Doesn't mean that they are always executing code. They can be more passive then. Sometimes there are again interactions with the program, but that means that memory management should more specifically also look at avoiding fragmentation problems, because if there are fragmentation problems, they would persist and would stay there for a long time. There's no way of healing them by restarting the program or something like that. So that's why we designed a specific garbage collector for Motoko. It's an incremental garbage collector. The idea is it's very much inspired by the Java Shenandoah's garbage collector, I guess one of more modern garbage collectors. It has snapshot at the beginning, incremental marking, the evacuation compaction phase, and uses Brooks forwarding pointers to do its work. However, it has certain differences that comes to these specific requirements. One is that the old GC phases are unbounded, which isn't the case in these more classical mainstream incremental garbage collectors. On traditional computers, you may afford to have certain phases that have not like a bounded phase. Typical such phases are, for example, scanning scanning the root stack. There's an extra updating phase, which I explain later on why we have that. And of course, the performance model is a little bit different. It is tuned towards the blockchain cost model. From the implementation perspective, the garbage collector work is the increment. The GC increments are interleaved in a deterministic way. Of course, at the end of the transactions, we also keep the liberty to move them within the transactions, just to mention that the very start of a GC run and the end of a GC run, that's what we require to happen at the end of the transaction. Of course, the increment have to have a strict number of instructions as bounding limits in order that they can fit into the transactions. And there's a specific aspect in the WebAssembly, technical aspect, that we don't have access to the native call stack for scanning the root pointers or patching pointers that we may need to update during moving of the objects. That's why we can use, in our case, it's not that problematic because at the end of a transaction, the call stack is empty anyways. That's why we have chosen this implementation design. There are alternative design possibilities too. As usual with this evacuation compaction garbage collector, it's based on a partition heap by fixed size partitions for 4 gigabyte address space. We currently have 32 megabyte partitions. And simple because it's single-threaded, as I mentioned before. A single bump allocator for regular-sized object is working. We have special handling for large object-sized objects. When the garbage collector starts, the first phase is the marking phase. It's full heap scanning to deal with any cyclic garbage, even inter-partition cyclic garbage. It's a conservative marking phase. Using snapshot at the beginning, deletion barriers. That means whenever there's a write barrier, whenever we overwrite a pointer, then the overwritten, the old pointer, is taken into account for marking. New allocations are marked. And as mentioned, the design of the garbage collector just requires for that phase that when it starts, the call stack is empty, and that's actually one of these critical phases that are often unbounded in classical garbage collector. That's how we solve it very simply by just not having to do that due to the runtime model. By the way, we just use conservative marking as the idea because that allows us, once it has started with an empty call stack, we can even continue with pointers present on the call stack. So if we want to have more fine-grained interleaving with the mutator, this would allow us to continue even to switch into the next phase, the evacuation phase, even if the call stack is not empty. The second phase, also fully incremental, is evacuation phase. There we have the freedom to focus on partitions. We can select partitions that we think are worth to compact by moving out the live objects that have been marked into new partitions, fresh partitions. And we do that in a very conservative way. We actually move all partitions that have at least a certain very low threshold of garbage. And if memory is scarce, meaning because that's copying, like it's a copying garbage collection process, and if we have not enough space, then we focus on just the highest garbage partitions in order that the evacuation phase does not exceed the memory, the free memory that is around. During that phase, as mentioned, it's also incremental, meaning that the mutator may continue to access, like to traverse pointers, look at pointers, and they may lead, of course, to old locations, and this is no problem here because due to these forwarding pointer techniques, every object that has a forwarding pointer in its header, meaning when an object has forwarded, it can be atomically redirected by just adjusting this forwarding pointer to the new location. The downside is, of course, that every load or store or even object referential equality comparisons involve indirections. In our case, that's quite cheap in that sense. We also implemented like the classical way of having conditional load burials, which proved due to this synthetic cost model of the blockchain to be more expensive, as we measured something like 27%. Once that phase is done, we have an extra phase, the updating phase, that actually scans through the whole memory and patches all pointers in the sense that no forwarding is anymore in use, so that all pointers lead to the most recent evacuated locations. And we terminate that phase by having, again, a call stack that is empty. That's also important, that we don't miss any like pointers that we can't scan. The reason for this separate phase is that typically garbage collectors leave that phase out and just combine it and piggyback it on the next marking phase. So when the GC schedules again, then during the next marking phase, this updating can just take place at the same time. But however, then we have this delay just to wait for the next scheduled GC round, and that may be a long time here on the blockchain. And also because we use conservative marking, that it's even more problematic because a new object allocation during the GC run have to retain at least this full GC run. So this proved to be have much faster reclamation. Measured some experimental results by having our own benchmark compared it to classical but production garbage collectors that we also have for Motoko, copying garbage collector, two-space garbage collector, a threading, compacting garbage collector, and two-generational garbage collector. This shows the GC pause limits for these 4 garbage collectors. The red line actually just shows the limit that we intended to have, and of course for the incremental garbage collector we can configure it that it exactly matches these limits. The counting is a little bit different. The garbage collector internally counts steps, not instructions, but we can linearly map these steps to instructions. The other garbage collectors have, for certain cases, have substantial longer GC pauses because the GC work is not limited to a fixed number. Also, comparing performance is a little bit different when it comes to runtime performance, because in the cost model there's this counting of instructions of the synthetic model, and this was not expected to be the case, but luckily we were lucky to reach that. The incremental garbage collector is not more expensive, it's even a little bit cheaper than the traditional garbage collector. This shows the average cost of running a program, mutated cost plus garbage collection cost. The reason for that is that for the incremental garbage collector, we have this liberty on focusing on partitions to evacuate. We don't need to do the full garbage collection job, but somehow can limit to what it's to the most beneficial aspect. Of course, then the GC throughput is similarly related. The incremental, it's as usual, like it's with a trade-off, comes with a trade-off, the footprint of the memory that is allocated. This shows the maximum size the program has ever grown to. It may still be that the memory is reclaimed, that some free partitions are around, but this is a little bit higher for the incremental garbage collector. That is expected. It's because of the forwarding pointers. that are in place. We also do not always evacuate all partitions. Partitions with very low amount of garbage stick around, so that also accounts for that memory. And of course, if we compare it to compacting garbage collectors, this is higher because we need this extra copying space to be there. But we can limit that, but this is this usual trade-off. Scalability, that was actually the reason for that, because on the blockchain we have like large-scale applications. People want to exploit the 4 gigabyte address space nowadays. They'll also plan to move now beyond 32-bit. And we see here this was taking the same benchmark, but only taking the cases where we can scale allocations. And we see here that it's possible to allocate way more objects with the incremental garbage collector, because in the classical garbage collector, we always hit this instruction limit first, because at some point there are too many objects, or the heap is too fine granular, or the space to be copied is too much, such that the GC work in total exceeds this transaction limit, and then it fails, and then programmers would have the trouble that it doesn't scale beyond. So to wrap up, I guess garbage collection on a blockchain is a specific niche that has different requirements to the classical, classical garbage collection. The emphasis on incrementality is much higher. It has really these strict limits, really similar to real-time garbage collectors in the sense that one needs to fit it into these transaction limits. Another aspect which I think is important, that compaction is relevant, because fragmentation would stick around with this conceptually indefinite runtimes of blockchain programs. Also, performance is a little bit different, to be tuned to maybe design choices that were good choices in a traditional computer perform a little bit differently on a blockchain. That's, for example, the forwarding pointer techniques works well. Another aspect is that we use mark bitmaps, which is typically avoided, but mark bitmaps somehow lower the amount of dirty page access and then help us to limit the memory image sizes, differential memory image sizes that the system takes. And to conclude, the Motoko incremental garbage collector has been specifically designed for this requirement, for these requirements. So thank you for attending the talk, and I'm very happy to take questions.
Okay, cool stuff. Happy to see this. One question, so you had this like number of 15% barrier for garbage to evacuate. Mm-hmm. Where's that number coming from? I would actually have expected a higher number. Or? Mm-hmm.
It's usually higher as far as, if I'm not mistaken, in the Shannon Dark garbage collector, it's much higher. It's like 60%, if I'm not mistaken. But I haven't looked at the recent code, but here it's like we measured what is somehow with regard to like this performance table, what is somehow like we didn't fit it immediately to that, but we didn't want to go further for the allocated memory to be there, because the allocated memory is an additional cost factor on the blockchain. That's one of those aspects like we considered.
That makes sense. Okay.
But it can be tuned. Like we're discussing that internally. So.
Right. Okay. Thank you.
In the beginning, you said that you store the memory image in the transaction, or did I get that right?
Actually, the transaction is the transition function. Like there's a memory image, then transition computation takes place. Computation is really like code that runs on this memory, on the main memory, but somehow the blockchain, when the transition has completed, then that state is decided. This is like a true state that is kept like for continuing computation, or roll back if there's something problematic about that or exceeded some limits. And then there's a new memory state that sticks around for that program. And so. Okay.
So the memory image, is it the whole memory?
Yeah, conceptually it's the whole memory, but technically it's a differential memory. That's why we are keen on having not like too many dirty pages. I just showed the logical perspective, because like this memory state is a little bit different on blockchain than traditional. Okay, thanks. And there's also like what people typically like, which can cause confusion, is it truncates history, so that there's really a need of doing garbage collection. Otherwise, the latest program memory image would continuously grow when the program has additional allocations. Then the allocated space always grows. You can never reclaim memory, and then these images like would monotonously grow. And garbage collection also helps in that regard. And history can be truncated, and it's really like reclaiming memory in total.
Last chance for a last question. All right, let's thank the speaker again.